Yes, welcome to electrical machine lecture. Now, we will today we are going to discuss cross and demagnetization in armature reaction. In the previous lecture, already discussed the what is the armature reaction. So just we will take the review because it is better for understanding. Armature reaction has armature reaction is nothing but the effect of armature magnetic flux over the main magnetic flux, and it is going to occur only the near to the maximum load or it's some appreciable load, because at no load condition or small load condition armature fluxes is very small, negligible, and it doesn't affect over the main magnetic flux. And because of this one, the effect of main magnetic flux, effect of armature magnetic flux gives the net reduction in the main magnetic flux per pole, and second effect is the distortion of the main field flux wave along with the air gap periphery or along the axis. So this figure A, under no load condition, armature does not carries any current. Therefore, the main magnetic flux is uniformly distributed over the periphery of armature or rotor circuit. Now, in the second case, armature carries some full load current. Therefore, armature conductor produces the magnetic flux, and the collective magnetic flux is shown here. And it is the total magnetic flux in the downward direction. So this is as per the right hand rule, we can find what is the direction of magnetic flux. So we found that under no load condition, this is the your main magnetic flux. It is given by FF, main magnetic flux, and this is geometrical neutral axis and magnetic neutral axis. So under no load condition, your geometrical neutral axis and magnetic neutral axis coincide to each other. Now, what is the magnetic neutral axis? It is the axis which is perpendicular to the magnetic flux. So here this is the magnetic flux and it is perpendicular. Now, when the generator is loaded, it produces the armature flux. So armature flux, the total armature flux is downward. The direction is downward. So it is for the figure B, it is shown. This is the armature magnetic flux. Now the combination of these two, that is the main magnetic flux and armature magnetic flux, it is shown that this is the main magnetic flux. Therefore, the total flux or the main magnetic flux, it is shown like this. So just by the red, say it is shown like this. This is the, here it is not uniform, whereas it is tilted. And because of this tilting in the main magnetic flux, the magnetic neutral axis gets shifted, because the magnetic neutral axis is the axis which is perpendicular to the magnetic flux. So here this is the perpendicular. So now under such condition, this is the say we can say that this is the downward magnetic flux, this is the armature magnetic flux, main magnetic flux, and this is the resultant flux. Now if we represent the same with the help of some vector diagram, so just it can be seen like that. This is the magnetic neutral axis, sorry, geometrical neutral axis. This is the magnetic flux direction. This is phi f as earlier, and this is the armature. Your magnetic neutral axis gets shifted. So here the magnetic neutral axis, this is the new MNA, MNA, and along this magnetic neutral axis, this is the total flux. Suppose this is the armature flux phi A, isn't it? And therefore the resultant will be like that, and the magnitude of the resultant magnetic flux phi r is smaller than the flux under no load condition. So this first condition, the first statements get satisfied, that the net magnetic flux get reduces. So this is the things which we have discussed in the last lecture. Now, what is the effect? The distortion, it is to distort the main magnetic flux, thereby causing the non-uniform distribution of the flux under the main pole. So because of the armature reaction, there is a distortion, and because of this distortion, the flux is not uniformly distributed, whereas it is get tilted. The shifting of the MNA, magnetic neutral axis, gets shifted. Why it is shifted? Because the magnetic neutral axis is the axis which is perpendicular to the magnetic flux, total magnetic flux or resultant magnetic flux, in direction of the rotation. Now it means that for the generator, whatever the direction of rotation, the MNA is going to tilt in the same direction. Whereas for the motor, the tilting of the magnetic neutral axis opposite to the direction. Suppose this is the direction of rotation. For the motor, it is going to shift in the opposite direction. This is the thing. Now, third is to reduce the main magnetic flux from the no load values due to the magnetic saturation. So this is the decrease in the resultant magnetic flux is going to observed because of the armature reaction. And what are the methods to overcome the armature reaction? So high reluctance of the pole tips, because at this tip side, the magnetic flux density will be more. And if we have the high reluctance to the pole shoes, definitely the magnetic flux distribution will be remain same. This is the one thing. Second is the reluctance in the armature flux. So as this is the path of the magnetic flux, suppose if you make the some cavity in the pole core, under such condition, the magnetic flux, it will offer the reluctance to the magnetic flux created by the armature reaction, and hence the reluctance is going to occur for the armature reaction, armature flux. So this is the reluctance will be more, and when the reluctance will be more, the creation of magnetic flux will be smaller, and hence the armature reaction. The third point is the strong magnetic field. So if you produce the strong magnetic field produced by the main pole, definitely it does not going to affect with the armature flux. And interpole, we are going to mount some pole in between the main pole. So this is, suppose this is the north and south pole are the main pole. We are putting some poles over the in between to maintain the uniform flux distribution over the air gap. So, and the second is the compensating winding. The compensating winding is the increase in number of turns in the field winding, which is going to distort. Means we will going to calculate how many number of turns are needed to compensate the effect of armature fluxes. Whatever the armature flux is going to create, it will create the same amount of magnetic flux by the compensating winding in opposite direction, or it can going to neutralize, or it is going to compensate. So this is the meaning of the compensating winding. Now, in this topic, we are going to estimate how many numbers of conductors or the coils are going to produce the cross magnetizing, means it is going to disturb the main magnetic flux, and how many conductors or coil are going to produce the demagnetizing effect. So now, say for our simplicity, we are considering this diagram. And this diagram, suppose this is the direction of current. This is the direction of current, means the current toward us for this one. And whereas this is the direction of current in the opposite half of the geometrical neutral axis. This is the geometrical neutral axis. Whereas because of the armature reaction, the magnetic neutral axis gets shifted. So this is MNA, magnetic neutral axis. This is the direction, this is the rotation or the direction of rotor. And this is for the generator side, because in the same direction. And if you consider in the motor, so it is in the opposite side. So this is the magnetic neutral axis for the motor. Let the angle between these two is theta, and this is also angle, the same angle we have make forward, and it is shifted the brushes. So now the brushes are here instead of, because the brushes should be on the magnetic neutral axis. And why it is to the magnetic neutral axis, we are going to discuss in the commutation process or end of this discussion. Now, because of this one, if you hold the conductor by right hand, thumb shows the direction of current and your finger shows the direction of magnetic flux. So this is going to produce the magnetic flux in this direction. So this number of conductors are going to produce the, this is also opposite one. This is, okay. So we will not showing this one conductor. So these are the conductor which is showing the magnetic flux in downward direction. This number of conductors produces the magnetic flux in the downward direction, and hence this is the main magnetic flux FF, sorry, phi F, and this is the direction of magnetic flux phi A, as it is already discussed in the previous section. Means the number of conductors under, say, if you give the name for our simplicity, let this is A, this is, say, B, now this is C, and this is D. Like this is O is there. So A, O, D and C, O, B, whatever the number of conductor over there, it is going, these conductors are responsible to produce the magnetic flux downward, and we have given the name as a cross magnetizing because it is crossing the direction of main magnetic flux in this way, and it is going to cross. So this is this number of conductors are producing the cross magnetization. Now again same, this is your geometrical neutral axis, this is your MNA. Because of the armature reaction, your MNA is going to shift it. Therefore, we are placing the brushes along the magnetic neutral axis, because at this magnetic neutral axis, the EMF induced in the conductor is 0, and it does not produces the sparking over the brushes. So the EMF induced at this point is 0. So the reversal of current is also going to take place at this point. It does not produce any sparking over the brushes, which will avoid the roughness over the surface of the commutator segment as well as in the brushes. So therefore, the brushes are always placed along the magnetic neutral axis, and we have to calculate how where will be the at what angle there will be the magnetic neutral axis to be shifted. So again, this is theta, this is theta, this is the forward angle and backward angle. Now see, when there were no armature reaction, the conductor's direction of current is downward, means it is going away from our side. So these number of conductors earlier in the influence of north pole, but it is going to appear under the influence of south pole. Means these two conductors, let this magnetic neutral axis at the geometrical neutral axis, and because of this shifting of the magnetic neutral axis and geometrical neutral axis coincide to each other, these number of conductors under the influence of north pole, whereas these number of conductors under the influence of south pole. But because of the armature reaction, some number of conductor which was earlier under the influence of north pole comes under the south pole, and vice versa. Means earlier, because of the no armature reaction, the number of conductors comes under the influence of south poles, now come under the influence of north. So these are the conductors which are having current direction is like that, means it is inside the screen, whereas the conductors, they are having current direction out of screen. So this is dot, this is dot, this is dot. Now apply your right hand rule. Just hold the conductor in your right hand in such a way that your thumb shows the direction of current, then the finger shows the direction of magnetic flux. So definitely the direction of magnetic flux will be in this way. So this is the direction of magnetic flux. means this is the direction of magnetic flux. This is opposite, okay, to the creation of north pole flux. Similarly, if you hold the conductor in such a way that the direction of current toward your thumb, this is the direction of magnetic flux. Means the magnetic flux produced by these number of conductors which occupy the position A, O, B, this is C, O, D. So under angle AOD and BOC will produces the magnetic flux opposite to the main magnetic flux. So we can represent it by in this way. So this is the main magnetic flux produced by main field winding phi F, whereas it produces the magnetic flux in opposite direction. It produces the magnetic flux in the opposite direction. No doubt, the magnitude of the flux produced by these number of conductor is smaller, but it produces this one. So it produces the armature magnetic flux in the demagnetizing effect because it is going to demagnetize. Whereas here it is going to produce the cross magnetize. So this is the difference. And now it can be, say, we can understand or we can discuss the same thing with the help of this diagram. So see here, this is the north pole. The fluxes are created from north towards south. So this is the direction of magnetic flux. Now the number of conductors earlier under the influence of south pole comes under the north pole and comes under the south pole. And the number of conductors which was earlier under the number of conductors which were earlier the influence of south pole comes under the north. So these number of conductors are producing the magnetic flux opposite to the main magnetic flux. So this is called as a demagnetizing armature MMF or armature fluxes are there. So we can represent phi A. It is the armature magnetic flux, but it is the cross magnetizing. Whereas these number of conductors under this is going to produce the magnetic flux is downward direction, but the flux is going to produce by the armature. It is phi A, but it is in the cross magnetizing. Sorry, it is a demagnetizing. So D and it is C. So the same diagram is that, and this is the new position of the magnetic neutral axis. Now here it is important to estimate how many conductors are responsible to produce the demagnetizing and how many conductors are responsible to produce the cross magnetizing. So we will see one by one. Say, we'll consider the same nomenclature. Let Z is the total number of armature conductor. Armature conductors. Okay. Let I is the current in each armature, current in each armature conductor. Okay. Which is equal to IA upon 2 for wave winding, whereas it is IA upon P is the lap winding, for the lap winding. These are the number of parallel paths. So the current is equal to IA upon P is there. Now theta M is the forward lead angle. Let as per the direction of rotation, we are considering the lead angle. Now total number of armature conductor in angle AOC and BOD. See, AOD, sorry, AOC and BOD. This is, sorry, it is a yes, AOC for the first figure. This is for the first figure. Okay. These are the AOD and BOC. So we are considering the this much angle, which is equal to theta m. So it is 4 theta m divided by 360 into Z. Means total number of conductor and the angle theta m for this one. So AO, sorry, this is AOD. It is not C, it is AOD and BOC. This is BOC. AOD and BOC. So this is angle theta m, 2 theta m here, and this is 2 theta m. So 4 theta m divided by 360 multiplied by Z. So now, therefore, total number of turns, So turns means two conductor will make 2 turns in these angle is equal to the same thing, only divided by 2. So 1 by 2 into 4 theta m upon 360 into Z. So which is equal to twice theta m upon 360 into Z. So these are the total number of conductors. Therefore, demagnetizing armature turns or ampere turns is equal to just multiply by the current. So current multiplied by the turns is nothing but the ampere turns. So twice theta m divided by 360 into Z into I. These are this one. This is, now if you take the per pair pole, so we can write demagnetizing ampere turns per pole or we can say that ampere turns for the demagnetizing equals to how which this is divided by 2 because there are 2 poles are there. So it is we will write in this fashion. So Z into I multiplied by per pair pole is there. So 2 theta I'm going to say not there, and therefore theta m divided by 360. So this is the required relation. It means that the number of ampere turns, those are responsible to produce the demagnetizing effect is this much. Once we know how many conductors and how much current is there, which is responsible to produce the magnetizing, demagnetizing effect. If you add the same number of conductor in series with the armature current, it will produce the same amount of magnetic flux and it is going to say neutralize. Therefore, it is called as a compensating winding. So we are writing here ampere turns. Say just to know the ampere turns, say this is the electromagnet and there are number of turns are there. Two conductor will make the one turns. So this number of turns, say n, and the current flowing in the conductors or the turns is I. So we can say that ampere turns is equal to n into I. Number of turns multiplied by current. So here also what we have done, first we have calculated how many conductors are there. The conductors divided by 2 will make the turns. So these are the turns. 2 twice theta upon z, twice theta upon 360 into z is the turns, which are responsible to do the demagnetizing effect in the armature reaction. Now we have multiplied by the current. This is the current. So it become a turns and current, ampere turns. So it become a ampere turns. Now what we have done, we have calculated per pole. So this 2 also become 1, and therefore these number of conductors, ampere turns, this much ampere turns are there, which produces the demagnetizing armature reaction effect. Now similarly we can calculate the cross magnetizing conductor. So we can calculate cross magnetizing ampere turns this is ampere turns per pole, isn't it? So this is ATD. Now we are going to calculate ampere turns for the cross magnetizing. So we have calculated the demagnetizing conductors are there. It is Z twice theta m upon 360 into Z. So if you subtract from the total number of conductors, see from this diagram. Now here we have calculated these number of conductors, isn't it? This one and this one from upper side and lower side. So if you subtract these number of conductor from the total conductor, we will directly get the number of conductors. Those are responsible to produce the cross magnetizing effect, isn't it? So we can write the cross magnetizing conductors per pole, which is equal to total number of conductor is Z divided by P minus the number of conductors, those are responsible for the demagnetizing. So demagnetizing already we have calculated Z twice multiplied by twice theta m upon 360. So it is equal to Z is common. So it is 1 upon P minus twice theta m upon 360. So these are the number of conductors. Now similarly, we can write, finally, we can write the number of ampere turns per pole. Therefore, cross magnetizing ampere turns per pole, that is 80 ampere turns for the cross magnetizing, just multiply by the current, so it become ampere turns, and per pole, so there are two poles are there, so divided by 2, so it is Z into I into bracket your this one, so 1 upon twice P minus theta twice theta, so only theta m divided by 360. So these are the number of ampere turns are responsible to produce the cross magnetizing effect. So this will our required equation. So this is very important one. So in this way, if we are able to calculate how many turns are there, which is producing cross magnetizing and which is producing demagnetizing, if same number of conductors or same number of turns, if we added in the main field winding to produce the same amount of magnetic flux, so armature reaction fluxes get neutralized, or it can get equal and opposite. So therefore, we can do the compensating winding. That compensating winding may be placed on the main pole or in the interpole, which we have considered. Now, we will see the commutation process. So as in the very early, early lectures of the topic, we found that whatever the EMF induced in the armature conductor is always alternating by the dynamically EMF induced. For the AC generator, if you use the slip ring, the current in the external circuit is bidirectional, that is a sinusoidal waveform. Whereas if you want the current in the external circuit is unidirectional, we are using the commutator segment and brushes. So with the help of commutator and brushes, it will conduct the current only in the positive half cycle, in every positive half cycle, and therefore the current in the external circuit or load circuit, the current is unidirectional. So with the help of commutator and brushes, the current get commutated, or it is in the unidirectional current. So the current induced in the DC generator is always alternating. To make their flow unidirectional, in the external circuit, we need commutation. So we need commutation. Why we are using the need commutation? Because we want the current in the external circuit in unidirectional. Then and then the machine is called as a DC generator. Otherwise, it is a AC generator. So just before the current coil reaches to the brush, if suppose this is the brushes are there, say these are the coils, these are the armature conductors and coils are there, isn't it? And these are connected to the commutator segment. So this is the commutator segment 1, 2, 3, 4, 5 like that. And this is the brush. So brush width is equal to the commutator segment, this one. And we are considering this line is nothing but the mica is there, or there is a insulation between these two segments. So these two segments are electrically isolated to each other and the coils are connected. So this is this one, and this is the direction of rotation. This is the direction of rotation. So brushes are stationary. So after some time, segment 2 is going to comes under the brush. Then 1 is going to comes under the brush position, isn't it? So just before the current coil reaches to the brush, it carries the current IA upon A. IA is nothing but the armature current in the conductors or a coil, and A is the number of parallel paths. Suppose in one direction, suppose the current is positive in one position. Soon after, the armature coil has traveled the brush with the coil current get reversed in the minus IA. So say here, it is this one direction and this is in this direction. Once it comes to the new direction, the current in the direction get changes. So half of the current is going to flow over here. We will see one by one. This reversal of current in the armature coil by means of brush and commutator bar is called as a commutation process. So what is the commutation process? By the commutation process, we want to reverse the direction of current in the armature in such a way that in the external circuit, the current should remain in the unidirectional. So the process of reversing the current and short circuiting the coil is known as a commutation process. Okay. Now this is the coils are there. This carries current in this direction, IC. Okay. This current in this direction, IC. So what is the total current? It is twice IC, and it will conduct in the external circuit is twice IC. This is the one position of the brush segment, isn't it? Now, once the brush comes here in this position, so half of the current, the same will be there, isn't it? Whereas the current direction, suppose this is coming over here. I think one more diagram is there. Yes. Okay. So in this direction, earlier, what is the direction of current? The direction of current in the coil B in this way from the right hand side. But half of the current is going to flow here and half of the current is going to flow here. It means that the current in the coil B get changes, isn't it? In this position. Now see here, the current direction is totally changed in the coil B. So this is IC and the current direction is as it is IC. Therefore, the total current again is twice IC. So here the reversing of the current is there. One more parameter, one more position we will take. If you consider that this is the commutator segment. This is the commutator segment. This is 1, this is 2, and so on as earlier. And here, this is commutator, this is the brushes position over this one. Okay, this position, not it is connecting over this one. Okay, so what happened? In this way, say 1, this is 2. So the current in these positions are IC, but here IC minus I2, and here it is IC as it is. So the current in this way will be addition of these two, and this one more. So twice IC minus I2 will be there, isn't it? Whereas the current I2 comes from here, So again, the current will be twice IC only. So this current is twice I2, this is I2. So under meaning is that when it is going to travel, the current in the short circuiting coil get reversed. Say from this one, the current in the B coil, there is the current in the B coil, half of the current comes here, half of the current comes here, and the total current to the external circuit will remain as it is twice IC as it is, isn't it? So the reversing is going to occur under the short circuiting of the commutator segment and brushes are there. And by this process, we get the unidirectional current in the external circuit. Now, suppose there is some delay and the current in the coil B is not reversed in the same time. What will happen? Some of the current is going to jumps from here, or it may be jumps from here. And this is called as a bad commutation, and it will produce the sparking. So sparking is going to produce if the reversing of current is going to take place somewhat delay in the short circuiting coil delay, and that's why there is a commutation. There is some sparking over the brushes. Therefore, we are shifting our brushes to the magnetic neutral axis. Under that magnetic neutral axis, the EMF in the coil is zero. It's zero. And that's why your brushes, the commutator brushes, should be at the magnetic neutral axis. Now, if your reversing of the current is not taking place in the brief period of the movement of the brushes are there, then it is called as a bad commutation. So either it is a over commutation or it may be a delay commutation. So let this current is positive IA and it is going to reverse at point B, it's going to become zero, means that half of the current from one direction, half of the current from the second direction, and the current get reversed in the minus side. So if it is occurring in this way, it is called as a ideal commutation. There is no delay in the commutation, there is no early commutation is there, and there is no sparking over the brushes, and it is a fruitful, or it will give the best operation of the DC machine. Either it may be a generator and it may be a motor. But if there is a delay because of the self-inductance of coil, because inductance is just like a inertia in electrical circuit. So it avoid to change the current. If the current is increasing, it try to oppose the change in current, means increase in current. Similarly, if the current is decreasing, it try to oppose the decrease in current. So in the commutation process, the current is going to reverse. And that quick reversal, there is a self-inductance, and because of this self-inductance, it gives some delay in the reversing of the current, and therefore it is called as a delay commutation. And because of this delay commutation, there is a sparking over the brushes. And similarly, over commutation also not desirable. So this is called as a say linear line is called as a ideal commutation. So similar to the to decrease, there are some methods to decrease the armature reactions. Similarly, here there are some methods to improve the commutation process. First is the resistance commutation, means we are providing resistance in the brushes and commutator segment, but sometimes it is not desirable because it will increase the contact resistance and brush drops are there and heat is going to produce. Second is the voltage commutation in EMF commutation. This also gives the best result if you are providing the EMF, if the same amount of EMF is going to induce in the opposite direction or injection of EMF. And second is the compensating winding, which we have already covered in this one. So this is the some process, it's an armature reaction and say commutation in the DC generator as well as DC motor. The process is same. The physical phenomena is same for the DC motor and DC generator. Only the difference is that the DC generator is going to deliver the current, and whereas the DC motor, it is going to consume the current from the mains. So thank you for listening this lecture. Next time we will see the characteristic of a DC generator. There are different type of DC generators are there, and so we will see in the next time. Thank you.